Well, we've come to a juncture in the course where maybe you would have some ideas just going into the lecture. We're going to be talking today about insects, both in medicine and research. This is something that has been on our minds for literally thousands of years, and insects have been part of our medical arsenal for that length of time. So I ask you up front if you have any ideas about what we might be talking about here. If you don't, fear not, we will give you the word. So let us continue onward. And we'll begin our discussion with insects and insect-based products as medicinal or therapeutic drugs. We'll then proceed to a discussion of insects and various kinds of research, often with some sort of drug emerging from that research with which we can treat human beings. And then lastly, we'll close with a very specific discussion as insects and their capacity as wound cleaners and wound healers, and finally, wound closers. Yes, there's just an abundance of literature on using insects to fix you up when you get cut or slashed or otherwise have your skin torn open. So this will be a fascinating discussion of insects in the real world as it relates to medicine. Now, if we focus first on insects as medicinal drugs, we're going to have a whole bunch of different categories to deal with. We're going to start with what the ancients did and engage in a brief discussion on the so-called doctrine of signatures, and then proceed to discuss very specific kinds of insect-based medicinal applications, which will include tannic acid, a product of various insects who make galls. We'll talk about that in more detail in a minute. We'll talk about insects as aphrodisiacs. Yes, insects for your love life. It's true. Again, dating back millennia, people have been doing this. We'll look at things that are found in insect blood that might have utility for human beings. These include things that have antibacterial activity. We'll look at insects as a very specific treatment for that scourge in mankind known as malaria. Yes, insects were used to treat malaria. And then finally, we'll look at some more recent interests in insects that include using insects as anti-cancer agents, insects as treatments for Alzheimer's, and other really debilitating conditions for which we have not so much in the way of prophylactic or preventative measures as well as things that can be used to treat or cure these maladies. So, as I mentioned, insect-based medicine has been on our minds for millennia and goes clearly back to the ancients, who were very aware of insects and often used them as a way to offer treatments against various different sorts of things. We have some really interesting stuff in the system of pharmacopoeia, which dates back to the 16th century, where it's recommended that you can staunch bleeding or ulceration from a open wound in the skin by using bed bugs. And of course they would think this because they saw bed bugs sucking the blood of humans, and they thought, well, shoot, maybe that has some sort of practical application. We can use it to staunch bleeding in wounded people and other animals. We also have the notion that we've discussed earlier in the course that insects, this is of course dating back to Lesser and his book entitled Insect Theology, the idea that insects exist for the benefit of mankind and therefore should have some demonstrable use even when they're doing bad things like sucking your blood. And so in that tome, which you read parts of, Lesser says, quote, "Every event in nature proclaims whatever happens is directed by a being, namely God, infinitely wise. From this principle it follows that God hath determined the uses of animals in general, and of insects in particular, and that he hath destined them to serve some one purpose, some other. It is not chance, then, that he hath made insects useful, but the eternal decrees of providence. And man hath only turned to his use what was originally intended for his service. So there you have it. Insects, even if they're biting you and gnawing at you and sucking your blood, are useful and good for mankind. So with this, it was a long-standing view that insects could be used medicinally and that they were created by God for man's use. And further, Lesser says this, but this is an older idea, that each of those natural beings was invested with some sort of sign that would explain to man what its use medicinally was. And this could be a physical sign like a shape or a color, or we'll discover also a behavioral sign. That was part of the insect's behavioral repertoire that would reveal its potential use as a medical treatment. And this is generally subsumed under the thing called the signature of signs, or the doctrine of signatures. In Latin, it is also known as similia similibus curantur, let likes be cured by likes. In other words, the plant or the insect that has medicinal value will have some shape or some behavior or some color that suggests its use, and that should guide how we procure and use these materials. So the doctrine of signs, or the doctrine of signatures, is a guiding statement of how things in nature can be used for the good of mankind. This is a doctrine that was advanced significantly by Pliny the Elder, and was certainly in use at the time of Galen. These are two people that we've already discussed, and you know that they were very important to the philosophy of medicine as it was developed early on. So let's begin with an example of the doctrine of signatures that may look semi-plausible to you. One of the leading and I think typical examples of how the doctrine of signatures looked is that plants particularly were shaped in a form that revealed their likely use in humans. Let's take an example. That would be, the classic example is the liverwort, which you see here on the right. So this lovely green thing is called the liverwort. It's a very primitive plant. It doesn't have leaves or branches like we'd normally expect. But if you look at the very tip of the liverwort plant, what you will see, I'm getting my little arrow up here to show you, the tips right here, they're lobed. They have lobes. And if you're an ancient and you compare it to the actual human liver, which you see over here, this brownish red thing is your liver, the lobes of the liver were allegedly similar to the shape of the lobes of the liverwort. And that's how the liverwort got its name, because the lobes suggested the human liver to the people who were naming the plant. As a result of the shape of the liverwort depicting in the ancient mind the shape of the liver, it was assumed under the doctrine of signatures that the liverwort would be good for treating maladies of the human liver, things like jaundice or hepatitis or nasty things that go on the liver. And that's how the doctrine of signatures, or the doctrine of signs, came into being and was used. Now, there are a lot of plants that fall under this doctrine, but it also extends to insects. And of course, that's why we're talking about it today. So the doctrine of signatures was applied rather liberally to insects. Again, this is captured in the phrase, let likes be cured by likes. And so what people would do is look around at insects. Here you see some lovely insects. But let's focus on this lovely fly right here. So it's a regular fly, a dipteran. And what you'll notice is that the heads of the fly they're basically bald, but they have these little spiky hairs every so often. So if you're an ancient person thinking about this, you think to yourself, well, shoot, if likes cure likes, and we've got this bald-ish fly with little, sparsely patterned hair, maybe we can grind up that fly with this baldness condition and apply it to the human head for those who are suffering from alopecia, which we also call baldness, and that would fix the problem. That would cause the hair to grow in the human. That's how the doctrine of signatures worked. Other examples of this would be things like singing insects, crickets, and so forth, cicadas, also lovely singers. They perhaps could cure maladies of the ear or the throat because of their ability to, their singing ability was thought to overcome lack of ability to talk in the case of somebody with a sore throat, or lack of ability to hear, as in the case of a person with an earache. So that's how this worked. And if you look at Pliny the Elder, whom we've referenced earlier, you'll see some lovely recipes for curing baldness. For instance, from the Historia Naturalis, we have the recipe here. The heads of flies applied fresh to the bald place is a convenient medicine for said infirmity and defect. Some use, in this case, here we go, the blood of flies. Others mingle the ashes with ashes of pear. Who wouldn't do that? Used in the old time, or else, if not that, then nuts. With this proportion, that there be a third part only of ashes of flies to the rest, and therewith for 10 days, not 10, not 2, not 12, but 10, together rub the bare places where the hair is gone. Some there be, again, who temper and incorporate these said ashes of flies with, wait for it, the juice of the colewort. The colewort certainly recommends itself for use in baldness treatment, and breast milk. Why not? Why wouldn't we put breast milk in our recipe for curing baldness? Others take nothing thereto but honey, which I assume has something to do with the fact that honey bees are very hirsute. They have a lot of hair, and that might recommend them for use in this cure. And indeed, that comes up later in Dr. James' Medical Dictionary, which dates back to the 18th century, 1743. He says, we shouldn't be focusing on bald insects to cure baldness. Rather, we should focus on things with lots of hair, like honey bees, and from them mash them into honeybee salts, which is mixed with some sort of unguent or gel, and apply that to the head to cure the alopecia from which some people suffer. So we have, differing opinions on whether we should go for something that looks bald to cure baldness or something that looks hairy to cure baldness. There's just all sorts of controversy when it comes to using insects and plants to treat human disease. As I said, the doctrine of signs or signatures also commends things that make noise to treat different kinds of maladies like sore throats and ears. There are specific injunctions, for instance, among Jewish women to use locusts, to put them actually in the ear to prevent an earache, which sounds like a really dumb idea from the modern perspective, but back in the day, you use what you have on hand. And of course, we have recipes from various other places, such as India, prescribing ointments that can be made from male crickets to control screaming fits. Because, if somebody is making lots of noise, then we take the insect that makes lots of noise, you grind it up, you apply it, and maybe that will stop the screaming fit. There are other interesting notations in the history of using insects to fix various human problems, one of which is the earwig. Now, we're not sure exactly whether the use preceded the naming of this bug or whether it came afterwards. It's probably the latter. The earwig was suggested to fix hearing problems by taking the insect, drying it, pulverizing it, and mixing it with, yes, of course, the urine of hare. Who wouldn't do that? To cure deafness. Now, the name is important because if you look at the insect, there's nothing about it that says, use this to fix your hearing problems. So the name probably is what recommended it for use as a hearing treatment, but biologically, the earwig has nothing to do with the ear. There were ideas that earwigs invaded your ears, human ears, and did bad things, but there's nothing to support that biologically, so it was probably all a matter of conjecture and uninformed by actual facts, but sometimes these things live on past their natural expiration date. We also have some signatures relating to insects that derive from the behavior of those insects instead of the actual appearance. Insects have been often used to enhance fertility or increase virility. Termites and ants are particularly favored as aphrodisiacs, things that might increase your ability to reproduce. And this probably relates to the numerous offspring produced by these types of insects. Another old tried-and rule, theraputant, that is insect-derived, comes from thistle galls. These are galls that are produced by insects that feed on various kinds of plants, and the insects, in the course of chewing on those plants, inject chemicals that cause the plant to form a gall or a big swelling in the plant. And sometimes these galls are loaded with particular kinds of chemicals that have specific kinds of medical applications in humans, and some of these actually work. So we'll look at some of these in a moment. As I mentioned, the galls have commanded human attention because they're very obvious. When the insects that produce the galls in the plants are busy doing their feeding activities on the plants, it causes the plant to produce these very large swollen places, which we call the galls, and as I mentioned previously, these are frequently filled with chemicals that the plant itself produces, and those chemicals may have a therapeutic benefit in human medicine. So here we see a variety of galls on different types of plant structures. These are leaf galls. These are galls attached to the stem, but you can see how big they are, how obvious they are. This is a gall that has been cut open, and you can see that there is a lot of fluid-filled tissue in here, and it is the fluid that is of medical use to humans. So in the case of the Aleppo gall, the substance inside the gall is called tannic acid, and it has a number of medical uses. It has a use as an astringent, which means it staunches bleeding, and it can be used to treat hemorrhaging parts of the body. Now, it's not, if you have a huge gash in your flesh, it's not going to do much to treat that bleeding. But if you have a smaller insult to your flesh, let's say you cut yourself shaving, for instance, then applying tannic acid as an astringent might, in fact, help control the bleeding. It's also hypothesized to help control gastric bleeding, for instance, in the case of ulcers, because it causes the veins to constrict, and that reduces the bleeding. And because of this demonstrated efficacy of tannic acid, and the fact that it's derived from naturally occurring galls, there's been a fairly significant industry that involves collecting the galls and extracting the tannic acid from them. So this was alive and well in places like Turkey. As recently as the 20th century, there were a lot of people who went to Turkey, collected a bunch of galls, and extracted the tannic acid from them. But more recently, we have sources of tannic acid that are a little less trouble to procure. Right now, there are South American sources of tannic acid, and we can also produce tannic acid in the laboratory, so it can be produced in pure form, and it doesn't have to be extracted and mixed with the other stuff or purified. So one of the important things and interesting things about the tannic acid industry is that you see the little wasp that produces the gall, and the tannic acid is formed by the plant reacting to the activity of the insect. But if you open one of those galls, roughly 50 to 75% of the gall's dry weight is this chemical tannic acid, which is a super amount of chemical. It's really high. So the plant is heavily invested in making the tannic acid, and that's one of the reasons why we've used the galls for so long. The plants that produce them make a lot of it under the influence of the wasp. In 1945, we were importing over 500,000 pounds of those galls in order to get it. As I mentioned, there's a South American option now, and we can also make it in the laboratory, which is very important in decreasing the cost. Now let's talk a little bit about those lovely aphrodisiacs. Certainly the classic aphrodisiac that is insect-based is a chemical called cantharidin. It's made by beetles, and they're given the common name blister beetles because when they feed on materials, biological materials, they cause a blistering phenomenon. And there's a chemical in the beetle, and that is, of course, the chemical cantharidin, which causes the blistering to take place. So if you take the blister beetle and extract from it the cantharidin, you can apply the cantharidin to things that you want to blister. Now, why would you do that? Well, if you are a person who wants to have an active love life, let's say, and it was 2 centuries ago, you might apply or ingest the cantharidin because it will irritate the mucosa of your urogenital tract, particularly the bladder, also the stomach, and your gonads. And so the fact that the urogenital tract, both in males and females, could be affected by this was thought to be the reason why one would use it as an aphrodisiac. I note that it is highly toxic. It can kill you. And it's toxic at a low dose. Now, there are historical incidents in which this became a thing. For instance, the Marquis de Sade, you remember him. Way back in the 18th century, he decided to have a party with some prostitutes, and to press his case, so to speak, he administered cantharidin to them. He did so in an unregulated and inappropriately high dose, and so some of the prostitutes died as a result. And that caused some problems for him. He was sentenced to death at one point and later got off the hook. But before we had the modern drug Viagra, we had cantharidin as one of our options for increasing I guess the idea in using cantharidin is if you use it and your urogenital tract is affected, it causes an itching sensation. So what better way to cure itching but some sort of applied friction, which would in this case be sex, and that was why it was used as an aphrodisiac. It also has other uses, such as inducing abortion, because after all it is toxic. In men, we know that some of the side effects of cantharidin are abdominal pain, dryness of the mouth, pronounced thirst, painful urination, and sustained painful erection, which sounds really bad to me, but back in the day, I guess it was just the thing. As I mentioned, in the case of women, it causes irritation, itching of the ureters and the urethra, which perhaps could be vanquished by having sex. So goes the philosophy, at any rate. But here's the interesting thing. There's actually this sort of subfield of entomology called sexual entomology, which is not a joke, and it is based on the idea that you can use insects or insect-based products to further your love life. In fact, there's an abundance of scientific literature on the subject, which was thoughtfully collated for you by the woman we've talked about a couple of times in this course, Dr. Carol Anelli, who's also an OSU faculty member, and she and her graduate student did a thoroughgoing literature review of the use of insects and insect products as aphrodisiacs. And here is the main body of information that we have about this, and I'm not showing you this so that you'll memorize everything, but I just want to point out, the table goes on for quite a long time, that there are multiple, in fact, almost every order of insects has something that people have used medicinally as an aphrodisiac. It's been used in that way in a whole bunch of different places and over swaths of time. So China, Europe, more China, a little bit in North America, but we're kind of late to the game, and we were using lepidopterans. But look, wasps, termites, leps, silkworms, hawk moths, praying mantids, neuropterans, damselflies, dragonflies, crickets. All of these things have been used by somebody at some time for some reason. They can vary from sexual stimulation, as in this case, to a love charm. You anoint your intended with a love charm to increase their ardor, to stimulate erections, another one, to prevent premature ejaculation, to increase the attraction that married couples have for one another, et cetera, et cetera. It just goes on and on and on. So if it's out there, I think it's safe to say that somebody somewhere has tried it as an aphrodisiac. All right, moving on. We have some interesting developments in modern times in the notion that insects themselves can be used for antibiotic purposes. Now, in ancient Rome, the bedbug, as we previously discussed, was recommended for this purpose, and that was because it obviously sucks blood, and therefore was thought under the doctrine of signatures to have some use in treating blood, and so it might be used or recommended as an antibacterial agent for that purpose. But more recently, we've discovered that within insect blood, the bedbug is one example of this, there are actual chemicals that have antibacterial effects, which means it kills bacteria, or bacteriostatic properties, which means it suppresses the growth and cell division of bacteria. And so there are actual insects with real antibiotic materials within them that can be used for this purpose. In the case of bed bugs, we know now that the reason that the females have antibacterial chemicals circulating in their blood is, of course, that their reproduction requires that the female's abdomen be ripped open and therefore will be exposed to the atmosphere, and any bacterial cells circulating in the air that are toxic or can replicate in bed bugs would thus be able to get into the female. So to protect herself, she's got antibiotics circulating in her blood to kill any such bacteria that might get in as a result of traumatic insemination. Other insects have other kinds of bactericides in them. Cecropin A is another specific antibacterial product that kills bacteria and can be found in some lepidopterans. So having a wanton, indiscriminate sex life is that you might get a venereal disease, of which syphilis is a very common example. And it's extremely debilitating because if it's untreated, it can invade your nervous system, causing insanity and perhaps even death. So there's been an awful lot of interest in finding ways to treat syphilis over the millennia. And one of the more interesting ideas was that because people understood, in recent times at least, that the organism that causes syphilis, which you see here, courtesy of Cornell University, it's heat sensitive. So if you can heat it up to a high enough temperature for a long enough time, it will kill the organism that causes syphilis, and you can be cured. So the next question was, well, all right, if that's the case, how do we heat people up so that they can rid themselves of the syphilitic parasite? And somebody had the bright idea, hey, I know, we could just infect them with malaria, because what heats you up better than malaria? It causes these recurring fevers every couple of days. It lasts for months and months, maybe even years. So over the course of having a case of malaria, you might be able to cure your syphilis, or so went the idea. We've learned an awful lot about syphilis over the last 2,000-3,000 years. In 1905, we actually located the organism, which you see over here, the spirochete that causes syphilis. We've tried all sorts of interesting ways to treat syphilis, including the use of arsenic, which was actually a replacement for mercury. Now, if you know anything about these two elements, arsenic and mercury, you know that they're both heavy metals and they're both very active nervous system poisons. So in both cases, the cure was likely to be as bad as the disease. But as I mentioned, in 1917, people learned that the spirochete that causes syphilis can't survive above 40 degrees Celsius. And as a result, ta-da, here comes the fever therapy to treat syphilis. So what would they do? They would simply take the stuff, the malaria-infected mosquitoes. They could mash them up and inject them, and that would cause the person to end up with a malarial fever, which potentially could kill the spirochete. I don't have any data on how effective that was, but it certainly was imaginative. Fortunately for everybody, in 1928, penicillin was discovered, and the spirochete is sensitive to penicillin, or it was. Like all microbes, the reality is that our overuse of antibiotics is leading to rampant resistance. So here's yet another reason not to overuse antibiotics. Moving on, we've got some fairly recent information that we can use drugs from bugs for all sorts of creative things. And we have a lot of scientists who are actually plumbing the insect kingdom for useful products that come from insects. And this is not a trivial undertaking. This is not something that is on the fringes of science. Rather, very reputable and high-profile institutions like the National Science Foundation, Merck Index, a serious pharmaceutical company, and the National Institutes of Health are all funding research in this area. And of course, there are a whole bunch of advantages to using insects, not necessarily as a source of drugs that would enable us to treat human maladies, but as a model system in which we could perhaps take experimental drugs, put them into an insect, treat an insect with them, and see what the reaction of the insect was. And because we can get insects in large numbers, and there aren't any major groups that are worried about us abusing insects in experiments, we have a lot of reasons why insects might prove to be a great model system with which to work. They don't cost that much. They're relatively simple, and yet a lot of the systems found in insects are biochemically the same as those systems that are in mammals. And so we can use insects as a very simple way to investigate the likely effects that things may have in mammals. And this is particularly true of chemicals that have some sort of activity in the nervous system. In humans, the nervous system is notoriously hard to study. A, because we're dealing with humans, so we can't do a lot of things that are invasive. And B, because we, particularly in the early stages of investigation, we don't know what the ill effects might be, and so it's really easy to go over the therapeutic dose and cause serious harm. So if we could use insects to forecast the likely effects in humans or other animals, it could be a really good thing. Now, to that end, we won't bore you with making you come up with your own ideas. We'll just plow right on through. There have been various studies, several of them by the agencies I highlighted on an earlier slide, in which we have compared the genes found in diverse organisms like yeast, flies, worms, and mice, compared those to humans. Now, the idea here is if we can analyze the entire genome, all of the genes in each of these organisms, and compare them to humans, then we can figure out which genes these various organisms hold in common. And that would then guide our choice of drugs and have other implications for how we would proceed to find human cures in other species. Here's a couple of examples. I'll discuss two examples, starting with this one, which appeared in Nature News a couple of years ago. And it addressed the issue of nanoparticles and asked whether or not insects might be able to transport nanoparticles in the environment. Nanoparticles are super small. Nano comes from the denotation 10 to the minus 9. So it's a really, really teeny tiny particle. And because of the very, very, very small size, it is not governed particularly by gravity, which is mass related, but rather by adhesive and cohesive forces. So nanoparticles could potentially stick to or adhere to the bodies of flying insects and then be transported away from the site of application to distant places, pretty much like DDT has traveled around the globe, but in this case disseminated by insects themselves. So because nanotechnology is based on the manipulation and also manufacture of particles that are really, really small, or even single atoms, when we use nanoparticles as drugs, often we want to have them as small as possible because we want them to be able to circulate in the blood. We don't want them clogging your arteries, and we want them to be able to cross the blood-brain barrier to have their effect. And for these reasons, for all of these reasons, these things are teeny tiny, as small as possible, intentionally, because that's how they potentially exert their therapeutic benefit. But because they are so small, it can lead to different behavior than in the macro world, and that's the nature of our concern. So scale is a big thing in biology, and there may be unique things that go on with nanoparticles as a result of their very small size. The transport by insects is just one of them. There may be other things like overt toxicity as a result of their very small size. We'd like to know about that ahead of time if we're going to be using these things and deploying them in an environmental setting. Because some of these things are really, really small, they have the potential to move through biological membranes. And that might be good if that's part of the therapy, but it could be really bad if it's simply a byproduct of their small size and not something we want to have happen. So there have been distressingly few studies that have looked at these issues, even though we are currently using and releasing these nanoproducts in nature. So why are we concerned? Well, release of those nanoparticles out there in the environment might lead to toxic responses, and they might be different than those that we see in laboratory-based toxicity tests. We know that nanoparticles can interfere with surface properties. They might be able to change the nature of your biological membranes, for instance, or they might lead to some sort of alteration in your cellular biochemistry that could be injurious to you because it is toxic. So what they did in this study was they used adult and larval fruit flies and they exposed them to nanoparticles. The particular nanoparticle that they used was 1/5000th of the width of a human hair in size, so teeny, teeny, tiny. And when they exposed the larvae to these things, they found that the larvae were not affected by eating food that contained those nanoparticles. However, there was a differential effect on the adults, which became incapacitated or died when the nanoparticles adhered to the surface of the adult flies and could not be removed by grooming. So this is a potentially really important finding, because one of the things that it showed is that those nanoparticles can spread from contaminated flies to uncontaminated flies. So let's assume we have flies that pick up the nanoparticles because, I don't know, let's just assume that somebody used a suntan lotion that sprays on your body and that the nanoparticles were part of the suntan's chemical composition. And in fact, this is true. Nanoparticles are used in things like suntan lotion all the time. So if a fruit fly happens to land on you after you've sprayed this stuff, it could contact the nanoparticles and carry them off and spread them among its buddies. The important thing is that there are naturally existing mechanisms by which nanoparticles could spread, and if we have a nanoparticle spill, let's say that nanoparticles are being transported in a big truck, and the truck goes off a bridge and the stuff spills all over the place, well, that could be a major environmental insult for which we are really unprepared to anticipate the likely impacts. Also, there aren't any current regulations for nanotechnology, its use and deployment inside the United States. Because this stuff is already in use in things like sporting equipment, sunscreen, cosmetics, pharmaceuticals, and electronics, it's out there. And as these things hit the landfills, we're going to have potential for insects to carry them off and do things that might not be good for us. Now here is a synopsis of the comparison of the different species, the mouse, the fly, the worm, the yeast, against humans. And I'm not going to bore you with all this stuff, but here are a whole bunch of different genes that are involved in cancer production, genes that are neurologically oriented, genes that are involved in malformation of structures within the human body. And over here we have an indication whether the fly, indicated by an F, worm, indicated by a W, or yeast, indicated by a Y, have those genes in them. A plus means yes, a minus means no. And you can see, if you just quickly look down these lists, that the flies have a whole bunch of these genes, which means that they could be an exciting way to study things like cancer, neurobiological effects, heart problems, malformations, and so forth. And so this is your federal government research budget at work. Here's one example, again using insects, again using fruit flies, where this might lead. In this case, the fruit fly was used to study the potential for particular drugs to treat human Alzheimer's. How did this work? Well, there is a gene in both humans and fruit flies, apropos of the slide I just showed you. And it has been linked to the hereditary form of Alzheimer's in both organisms. Okay, you probably didn't know that fruit flies can get Alzheimer's, but they, in fact, can. And this is manifest in fruit flies pretty much the same way it is in humans, namely one of the first signs of this problem is memory loss. So the goal here was to figure out what's going on in humans by studying what's going on in fruit flies and maybe come up with therapeutic drugs in fruit flies that could be used in humans. Now the advantage of using the flies here, well, there are several. One is the life cycle is much shorter, a couple of weeks, so you can have lots of adult flies produced very quickly, and that's enormously useful. They're plentiful, obviously, and you don't have to access human brains in order to do the testing. We can't diagnose for sure a person with Alzheimer's until after they die, and you can go in and look at the brain and look for particular kinds of plaque and so forth in the brain that would be a signature of Alzheimer's. Obviously, we don't want to do that while the person is still living. And equally problematic is our ability to test drugs on Alzheimer's patients. However, we can genetically manipulate fruit flies to actively study and produce the Alzheimer's condition in fruit flies. And this is how it works, using a behavioral assay. What is done is you can take a virgin male, a male who's never mated with a female, and put her in a cage with a female who is already mated. Now, the female fruit flies are very chaste. Once they've mated with a male, she will not mate again. She will rebuff him. The male, being a virgin, unfamiliar with the ways of females, will court her, because that's what males do, but she's already mated, so she's going to tell him to hit the rails. She's not interested. She rebuffs him. So a normal male, one who doesn't have Alzheimer's, the male will learn, and he will carry the message that females can rebuff him over to the next encounter with the female. So if he's paired, the male who has now been rebuffed and learned from it, if he's paired with a receptive female, one who is not yet mated, even though she's receptive, he remembers being rebuffed, and he will not court her with much enthusiasm. He'll kind of test the waters. If she doesn't immediately turn around and yell at him, then he might proceed, but he's going to be very timid in his approach to her the second time because he was rebuffed the first time. However, if you have an Alzheimer's fruit fly, one that has been, in this case, genetically altered, because we can go in and mess with the gene that causes Alzheimer's, basically turn it on, and so now the male has been genetically altered to have Alzheimer's, and he goes through the same process. You put him in the cage with a mated female. He approaches her, but she rebuffs him. The interesting thing is, now that he has Alzheimer's, he's also lost his memory. So when you put him into the second cage with the receptive female, his courtship activity is as high as it was for the other female because he doesn't remember being rebuffed. So, it's a really interesting thing. It's a really interesting system. And this means that we can now take the Alzheimer male and we can treat that Alzheimer male with drugs that might relieve the effect of Alzheimer, in this case, memory loss. And one of those potential drugs, in fact, it's in use, is lithium. So you can take the Alzheimer male and treat him with lithium to restore his memory and also his ability to learn. And if you put him through the same rigmarole, he will remember this time, and he will not court the second female because he recalls having been rebuffed by the first one. So this means that potentially we could use this system, the Alzheimer's males, as a mechanism for testing other therapeutic drugs that might have the ability to restore memory loss or prevent it in the first place. So insects are really useful neurobiologically for other reasons. We can go into an insect and extract the nervous system pretty much intact. And we can keep that nervous system functioning by putting it into an environment that has buffer and stuff that will help hydrate it and keep it alive. And then we can use that intact nervous system to study the effects of potential therapeutic drugs that could be used for humans. And a lot of this is facilitated by the fact that we've done an awful lot of research on the nervous system, both in humans and in insects, and we know a lot about the mechanics of how the nervous system operates. And so we know, for instance, that there are ion gates that let sodium and potassium in and out of the nervous system that are really important. And we can find chemicals that open and close those gates on command. We also know, and this is a really important point, that these nervous system gates are evolutionarily conserved, which means that they're basically the same in insects as they are in humans. And as a result, scientists can exploit this fact and use that for our own purposes, which in this case is to find human cures for some really nasty conditions using insects as a way to do that. We also know that insects themselves can be the source of all sorts of interesting compounds, particularly toxins and venoms that have nervous system activity. And indeed, you can go to a standard biochemical catalog, in this case, neuroscience products in the ICN catalog, and you can find stuff like scorpion venom, honeybee venom, wasp venom as a thing that you can purchase to do research with. So there are a lot of avenues by which insects commend themselves for use in human drug research. Again, because we know a lot about how the nervous system works, this is a trace of an action potential in a control, a normal animal, and under the influence of one of these neurobiologically active insect venoms, and you can see that there's a big difference in these two curves, and that's just an indication of the activity of the, in this case, scorpion venom in the activity of the nervous system. So we have all sorts of data that buttress this claim that we can use insect-derived neurotoxins therapeutically in humans. And one of those things is this. We have a human condition called glioma. It's a kind of brain tumor that's really bad. You can see, in this case, we have the brain tumor here, and over here we see what the underlying cells look like. You can see how dense they are if you compare that to a normal brain histogram. You see that there are many more cells up here because of the cancer than there are down here, and that's really bad for the person who has the cancer. In fact, we've had an awful lot of high-profile people contract glioma, including Ted Kennedy and this guy, Robert Novak. Now, if you know either of these guys, you know that they are diametrically opposed to the philosophy of the other. Kennedy is a very liberal Democrat. Novak is a very conservative Republican. But glioma is an equal opportunity killer. It claimed them both. Every year we know that 24,000 people of glioma will be diagnosed, and a year later, 18,000 of those people will have died because it's very aggressive. Once you get it, it progresses very rapidly, and the disease is invariably fatal. We have very few examples of people who have contracted it and survived it. You can go through all the usual stuff, the surgery, the chemotherapy, the radiation, but in the end, under the current treatment regimes, 98% mortality will take place. So as a result, new treatments are desperately needed. And we might ask, well, why is this thing so lethal? And one of the curiosities about it, well, about glioma as well as any brain cancer, is that the nerve cells, the ones that make up the bulk of your brain, don't divide. So how is it possible for them to become cancerous when cancer is uncontrolled cell division? Well, the answer is that the gliomas don't come from the brain cells themselves getting cancer, but there's a protective layer around the brain that does have cells that divide, and the gliomas come from that protective covering becoming cancerous. And the cancer cells then invade the underlying brain tissue, which causes the problem. So the rate that the gliomas multiply make them very difficult to treat, and also the cells in the protective covering that are dividing too fast begin to invade the underlying brain, and it's really hard to remove all of this by surgery, so that's why we're stuck. Now, however, physicians have been working with the scorpion venom and doing a variety of different kinds of studies. One is to inject it directly into the brain, but that's pretty dicey because you can hit the wrong part, or you can inject a little bit too much, and that can have disastrous effects. One of the things they found is that the venom itself does not kill the glioma tumor cells, but this is the operative part. The scorpion venom does preferentially stick to the tumor cells, and as a result, it has the capacity to act as a magic bullet, in other words, as a delivery device, because it specifically attaches to the glioma cells. So what scientists have done, and this is incredibly awesome and tricky, is they use the scorpion venom as a delivery device, but they attach to the venom particular chemicals that kill the cancer cells. And because the toxin is attached to the scorpion venom, and the scorpion venom is only going to attach to the tumor cells, it's the literal magic bullet. It only kills the cancer cells, and that is one of the most profound advances in cancer treatment that we have, because radiation, chemotherapy, all of those things kill healthy cells, but they kill the cancer cells faster because the cancer cells are dividing quickly. But ultimately, that's what causes the nasty side effects of most cancer treatments, is that the healthy cells are also being impacted. But the scorpion venom then acts as a delivery device that takes the toxic material directly to the cancer cells, to nothing else, and kills only the cancer cells. And so this potentially is a really significant new treatment for human glioma. So here's our friend, the Israeli scorpion, which is the source of the venom. And I'm hoping that 5 years from now, this will be a standard treatment using scorpions. All right, we mentioned up front that we would move on to a series of slides on insects as wound cleaners. This is something that is at least a couple of centuries old, possibly older than that, but we don't have a lot of good literature to back it up. But we know that in World War II, in World War I, in the American Civil War, that the treating physicians in the camps noticed a curious thing. And that was that when they triaged patients, when they took the incoming patients and they broke them up into 3 groups, one of which could be treated and probably treated successfully, another of which was too far gone, and therefore they just would place them aside and not treat them because they felt they were too impacted, too far gone to command the materials and attention that it would take to treat them, and would probably be unsuccessful anyway. So what the physicians noticed when this happened, and this was particularly the case among people who had amputations or needed amputations but were triaged out and didn't get the amputation. What they particularly noticed was that the people who had the amputation did less well than the people who didn't get the treatment because they were considered too far gone, and whose wounds were subsequently invaded by maggots. So we'll see some actual insect wound cleaning going on in this series of slides. The reason that the untreated soldiers in the various wars were doing better than those who got the actual therapeutic treatment was that the invading maggots were secreting into the wounds that they were infesting antibiotic materials that cleaned up the wound and prevented invasion of bacteria. And so that philosophy has been put to use in the real world in modern times. When we get a patient in a modern hospital who has a wound that will not heal, after months and months of trying, going through different antibiotics, trying to find one that will work, and it still doesn't work, then every so often, when you get one of these cases, the physicians involved will make a phone call to a department of entomology, such as the one that we have at OSU, and request what we call medicinal maggots to clean up a wound that will not heal. So here you see an elderly patient receiving her maggots. Obviously, she's not looking at them, putting maggots into her wound. Who would? But here's the kind of difference it can make. This is a wound here that's nasty. It's still open. It's been treated for months. The leg is swollen. It's not looking good. a couple of weeks after the maggots have done their thing, it's starting to heal. The skin is starting to close, and this is a massive area to close on a leg. Legs are hard to close anyway because you're stepping on them all the time, and that tends to break the wounds open. So they're notoriously difficult to heal, but here we have the work of the maggots. The wound is closed, and the skin is in the process of healing. So in fact, in the United States, we have a sort of cottage industry in medicinal maggots. What we do is to raise the maggots in laboratories, and we raise them on a known food source. They're maggots, so they're interested in meat. And so the question is, what meat are we going to feed them on? Well, normally what we do is procure beef liver from a butcher and feed them on that. And then prior to use on a human being, we purge them. We have them eliminate the contents of their stomach so that we're not putting beef liver into a human wound. And you can see that these are, we have a mixture of eggs and first instar larvae here. Here are the larvae at a later stage of development, and this is a fairly mature larvae, probably the third or fourth instar as it goes through its life cycle. But you can see by the comparison of the size to the penny here that even the larger sized ones, these look like they're starting to pupate, are pretty small. So it's not like we're putting these huge gargantuan things into a wound. And so we have, a small but persistent market for what we call maggot debridement therapy. Debridement means to clean up a wound. So MDT is maggot debridement therapy. And it's accepted, at least in part, by the medical establishment, enough so that it is used pretty regularly, but not necessarily by your insurance company. So if you have maggot debridement therapy, your insurance may or may not pay. But the maggots exist, the people who raise them exist, and so maybe it's on its way to becoming an accepted therapy, we don't know. But the physicians involved still don't have a medical code for maggot debridement therapy, and if you're getting the therapy, the physician has no way of putting it onto the form that will charge your insurance company. So there's difficulty getting reimbursed, but the people who do this are now working with the American Medical Association to get an AMA code so that we can have maggot debridement therapy paid for by insurance. Now, if we talk for a few minutes more about the nature of how this all came to our attention, as I mentioned, back in some really important wars, including Napoleonic Wars, Civil Wars, and both World Wars, the soldiers who were triaged out of treatment because they were too far gone simply did better because they were invaded by maggots, which cleaned the wounds. And we know from further scientific research that what the maggots do is they remove, in a nasty wound, they'll remove the dead or necrotic tissue, or at least the good maggots will do that. They will specifically focus on the necrotic tissue and eat it, clean it up. They will not touch the healthy living tissue, which is a really important consideration, as we'll discover in a minute. So they get rid of the dead tissue, and also as they're doing their work, they're injecting the wound with a specific antibiotic, which we now know to be allantin. So in the 20th century, because of what we saw in wartime and the deduction that those not getting treatment did better because of the maggot debridement therapy they were receiving gratis from the maggots that were out there in the environment, people began to study many species of flesh flies to determine which ones would show the best potential for use in human beings to remove necrotic tissue. Obviously, we want something safe and simple. We want something we can raise in a laboratory in large quantities and decontaminate. You don't want to put flies in a wound if they have a load of bacteria themselves that would be injurious to that human. So because there are so many species of flies believe me, they're out there waiting for us, that could potentially be used for maggot debridement therapy. We need to know the underlying biology, because we'll find a whole bunch of related flies that have markedly different biological characteristics, and not all of them recommend themselves for use in medicinal therapy. So we have some, such as the caliphorids, that breed in dead stuff. We have others, such as the sarcophages, that breed in the dead or dying tissue. In other words, there's just a whole bunch of differences in the way these things act biologically. Some of them are what we call saprophages that can become facultatively parasitic. In other words, they invade necrotic tissues, but then can decide, you know what, this is pretty good eating, so let's dive deep and find out what's going on inside. So they move from the wounded tissue into the healthy tissue. They can sometimes travel in the blood and end up in different organs. You don't want those in your maggot debridement therapy. We need to know very carefully which kind we have and what they're going to do once they are put into the humans. We want them to invade the dead necrotic tissue. We want them to clean up the dead necrotic tissue. And it's great if they also secrete those antibiotics to prevent infection from taking place. We want the larvae to congregate in the wound. We want them to stay where we put them, where they're cleaning up the necrotic tissue. We do not want them to spread to healthy tissue, and we certainly do not want them to travel in the blood to other organs. We probably want them not to be host-specific. If they're technically maggots that grow in raccoons, but they're useful by every other criterion, it would be great if they also would grow in humans under laboratory conditions. So those are the kinds of things that we need to be concerned about. Also, we want them to have their activity fairly quickly, not prolong the agony for weeks or months. That would be awful. So all of these characteristics need to be considered as we choose species for this honor. Now, some of the things that we don't want for maggot debridement therapy are things like flies that only invade dead tissue. We want to get to the person long before they're dead. We don't want organisms that invade only healthy tissue. We're interested in the wound, not in the healthy tissue. We leave that alone. We don't want slow developing larvae because, as I said, if you're having this done, you want them to get in there, do their thing, and get out as quickly as possible. You do not want to walk around with maggots in your wound for months. So slow developing larvae are not going to work. Those that invade necrotic tissue, which is what you want, but then infect internal organs, yep, we don't want those. And females that are larviparous are not good because the larvae are too difficult to extract. And believe me, you do want to extract them when they're done. So here's a study by Sherman, who looked at the various families and species of different kinds of flies that could be used for maggot debridement therapy, and looked at their individual characteristics biologically and proclaimed that most of them are not suitable for use for one reason or another, but there are some that do recommend themselves for use. So we have options, and once we have the ability to specifically grow these things in a laboratory, we could potentially deploy them for use in maggot debridement therapy. So here you see among these sarcophagid flies a whole bunch of properties that are good for maggot debridement therapy, and as a result would be perfectly suitable for medicinal use. So, in general, the facultative caliphorids are most often recommended for use in maggot debridement therapy. There are several advantageous biological properties, like eating only the necrotic tissue, and the main species of use in commercial MDT therapy is this green bottle fly, also known as Lucilia serracata. Here we see another series of photos indicating how well this works. We have a chronic foot lesion down here. It's been unhealed, oh God, for 2 freaking years. And look at this ugly thing. Imagine how painful it would be to walk on that. So this person then underwent maggot debridement therapy, and initially it looks worse than it was, but it's actually in the process of healing because the necrotic tissue is being removed and the vascular tissue, the blood vessels, are being repaired. And that initially looks much worse, but in fact is a sign of healing. And then lastly, a year later, it's completely healed, and the guy is back on his feet again. So, it works. What can I tell you? And one final thing, this is a therapy that's both ancient and modern, and it involves treating open wounds. Imagine you're out in the field, you don't have any medical equipment with you. This is a treatment that indigenous people have known about for millennia and continue to use today. So if you are out in the field and you get a nasty gaping wound, which you need to close as quickly as possible, one thing you can do if you're in the right part of the world is to grab onto an Amazon soldier ant, which has huge mouth parts, huge mandibles. And if you position, you grab the ant with your hand and you position the ant over the wound in such a way that the mouth parts, when you do what you're going to do, land on either side of the wound. You then proceed to squeeze the ant, which irritates it, so it tries to bite you, and in the process of trying to bite you, it sinks its mandibles into your skin and pulls the skin together. So at that point, you break the body off the ant, and you have the wound partially closed. And then you repeat this with several other ants, and eventually this is what you end up with. Ant parts hanging out of your skin, but the wound is now closed, and it heals very nicely.